Welcome, everyone, to today's A16Z Research Crypto seminar. Very pleased to introduce our own Pranav Garimidi. By popular demand, this is going to be his second talk on block building, specifically today in Solana and other high-performance chains.
Yeah, super happy to be here and give follow-up talk. Yeah, so a few weeks back, I talked about kind of the transaction supply chain for Ethereum, kind of what it is, how it worked. We got a bit into Solana, but we didn't get too far. So today we're really going to dive into Solana pretty in depth, and with some time at the end, talk a bit about Aptos too. So yeah, so just reiterating, when we talk about the transaction supply chain, we're really trying to answer this question about kind of in practice, how do transactions actually land on chain? And so we've seen that for Ethereum now, where things move a bit slower. And so you have lots of time to run these different auctions and things can move kind of piece by piece. And today we're really going to focus on kind of when we try to scale things up and move to like a faster environment, what new challenges arise? In particular, how does Solana deal with these things? And so again, these are the three kind of main things we're addressing with the supply chain, right? The first one is MEV, right? So MEV kind of adds lots of different economic incentives to the protocol. And so in turn, many kind of subcomponents have sprung up and changed how transaction flows work to accommodate it. There's also just computational constraints, right? So even in Ethereum, block building was hard, kind of deciding about order of transactions. That's going to be even more so in Solana with kind of the faster speed and kind of more transactions they're dealing with. And then the same thing with the bandwidth constraints of, even in Ethereum, we kind of had bandwidth constraints of kind of how much can validators be expected to download and upload. We move to these faster environments that only gets exacerbated in kind of just the raw demand that these systems are trying to satisfy. And so the very simple version of this problem is just how does a single validator decide what transactions to include, right? They're kind of seeing all these things. They need some mechanism by which decides what gets included. And so we're going to talk about kind of what this looks like at the metagame level. You know, one thing to keep in mind, what types of preferences people have, right? They're not going to be simply just people that want to land at some certain price. While that might be a lot of transactions, there will also be lots of transactions where people have very specific constraints around, I only want to be included if the transactions doesn't fail. So this is also called kind of revert protection. Maybe you want to get some certain kind of guaranteed price when you get executed. You know, so there's various kind of very specific types of constraints people might have. And we want the chain to be able to kind of support these. And then separately, apart from just kind of the richness of preferences people might have, we'll also have that there's going to be just tons and tons of transactions. And it even might be the case that kind of there's more transaction demand in terms of just pure bandwidth that can even fit into a single validator. And so we'll see kind of how Solana in particular kind of addresses this. So let's get into it. Yeah, so just as a high level picture, this is kind of the whole supply chain on Solana. And while this might look like a fairly simple picture compared to the Ethereum one I showed you guys a few weeks back, there's actually a lot of interesting stuff happening inside these boxes that make the system pretty complicated. So let's start with the network layer. So we're going to kind of start talking about how do transactions get to the validator, how do they leave the validator. And the first thing that's kind of interesting on Solana is this notion of stake-weighted quality of service. And so here, the problem really is that there's more incoming transaction demand from a bandwidth perspective than the leaders have capacity for. So Solana doesn't have a mempool. And so the protocol is that everybody directly sends their transactions to the current leader or kind of the next set of leaders. So those leaders can like immediately include those instead of kind of just gossiping transactions around for a while. The problem with that, as you can imagine, is that there's just way too much stuff going to the leader, that the leader has some fixed amount of ports, some fixed amount of bandwidth, and this can very quickly overwhelm how much capacity the leader has. And this was fine for a while of kind of people on Solana dealt with it. And then about, I want to say kind of 8-9 months ago, or kind of around that time frame, there was this thing called OR that spun up on Solana. And it's basically this like proof of work smart contract, where the more transactions you spammed into this thing, the more money you would make. And so now there was actually this like massive economic incentive to just be like spamming transactions to people. And basically the network started having problems of there was so much demand to spam the validators that normal transactions like just weren't even being seen by the leaders, right? The leaders were had their ports completely filled with these kind of garbage transactions. And there are even incentives for kind of adversaries to basically just DDoS the leaders and to just fill up all of their capacity with their own transactions as possible. So leaders like couldn't even include kind of these adversaries, competitors, transactions. And so kind of the hot fix Solana approach this with is what they call this quality of service. And the basic idea is that instead of allowing kind of anybody to connect to the leader, every node gets a connection whose size is determined by their stake, right? So if you assume that I had 10% of the stake, then the next leader would maybe dedicate kind of 10% of their bandwidth personally just for my transactions. And so in practice, it's a bit different. There's a split between what they call kind of staked connections, unstaked connections. So it's not the case that if you have no stake, you can't get in at all. Nodes are supposed to reserve kind of some fraction of their capacity for these public connections. And so that's kind of this circle at the bottom. But the majority of the connections really are for kind of the staked nodes. And so it's RPCs, it's other validators. You can imagine kind of any party that wants reliable transaction inclusion kind of often either contracts with the party that has lots of stake or themselves has a lot of stake to kind of get included. And now one natural question you might ask is, how is this enforced? It's not really. And so the way it works in the protocol is it's literally just kind of a file that kind of is like, kind of a mapping between different addresses and how much stake they have based on kind of what's on the chain. And it's expected that kind of the default client follows this faithfully. There is nothing in the protocol that stops any kind of validator from overriding this file and inputting whatever connections they want. And in practice, that does happen actually. And so how faithfully the protocol kind of follows kind of the stake-weighted QoS is kind of up in the air for right now, at least. Kind of initially when they rolled it out, everybody was using it. Now there's kind of a mixture of how different nodes allocate their incoming bandwidth. But I think the main takeaway being of that even at this level of abstraction of kind of how do nodes decide who to listen to and how to get transactions even to be considered to the validator is in itself kind of an economic process on Solana. It's something I think kind of any chain that's operating at this kind of capacity needs to face at some point.
And so the tension here is that some of the transactions, there's transaction fees. So if you just follow that, you may be leaving some transaction fees on the table. Is that the main tension about whether to do this or not? Or
so I think you have to do something. So there's also centralizing concerns here, right? So even the notion that I need lots of stake to like lend a transaction is undesirable. So it's really, you need some kind of economic back pressure on the entry point to the validator. So the transaction fees is less of a concern. Like the highest transaction fees probably are going on the staked leaders, and that's probably okay. It's more so in some notion of fairness or efficiency in the sense of, if a few RPCs or validators get lots of the stake, do they have outsized market power and kind of dictating other terms in the market structure? And so that's not ideal. And so people have been thinking about different ways to address this. But at least as like a first fix, this is kind of what they came up with.
Yeah, but you could imagine a fee-based back pressure, right?
You could. So the tricky thing is this all happens before execution, like before anything happens on chain, right? So there have been ideas floated of like the validators auction off kind of their incoming bandwidth kind of some blocks ahead of time. That could work. The concern is that it's very hard to enforce the validators actually following the agreements they gave. Or so say a validator like ran some auction and they permissionlessly sold off 20% of their incoming bandwidth to like some nodes. Then it's hard ex post to verify if those nodes don't get the transactions in. Is it because they were faulty? Was it the leader was ignoring them? They were fulfilling their commitment? It's just kind of in a permissionless setting, it's hard to actually verify things at the network layer before you can actually run them on chain.
So this allows you to kind of do side bets outside of the fees in some sense.
Right. Yeah. So everything here is kind of outside the protocol. I think it's an interesting open problem of kind of to what extent can we meter at the network layer in a permissionless way without these kind of more standard like legal agreements and other things. Yep.
So like if my transaction doesn't get in this block, like will I have to resend it to the leader of the next block like myself? Or is there a way to directly forward this for transactions?
Yeah, so validators in Solana do forward transactions by default. Now that doesn't always work. Like you probably would. I mean, it depends on the use case, right? So in some cases, if you're not super concerned about execution and you just like, don't want to be sending too many times, you can probably rely on this. RPCs might do it for you. It's kind of there's various solutions to it. But yeah, so I'd say it depends on the use case, but by default it should be forwarded.
So I thought you will just send to the next X validators or N validator,
Yes.
right? The RPC themselves.
Yeah.
Whenever they send, then send next validator. So in that case, we won't forward, right?
Leaders anyways forward. So yeah, so it's like there's room on the table for optimizing this, and people have definitely talked about it. So the default behavior, or at least I still think is what they do, is that a leader will forward the transactions they didn't get to the next leader. But RPCs anyways send stuff to the next leaders. So typically there's tons of duplication. Like the network is being spammed by tons and tons of transactions, and there'll be a graph later on. I'll show showing that more exactly. But yeah, there's tons of duplicated things where there maybe just don't have to be, just because people want to like really be sure their stuff gets in. They'll send it through like kind of all the paths possible.
You said that there's a smart contract on chain that if like there's like proof of work and then I get
Yeah,
money
this
from
was
it?
some like random app somebody did. Like it's not part of the protocol.
I
It's
see.
just-
Oh, okay.
Yeah, somebody just made some application that was like, I'm going to make this fun game, or I don't know, and then people started using it and stuff like this. So this is kind of the outgoing bandwidth. So it's called Turbine. And so Roger also spoke about this a few weeks back as part of Alpenglow. There's a new version of this that's going on called Rotor. It's basically the same idea, but what's in production today is this thing called Turbine. And this is basically this observation that when you're disseminating data, you should probably do it kind of according to stake as well, and that you want kind of the highest stake nodes to hear about transactions first. And so basically what Solana does is kind of when they're producing blocks, they erasure code these blocks up into chunks, and then they send this in this basically stake weighted tree, where basically the more stake you have, the higher in the tree you kind of expect it to be. And here I'm showing a fan out of 3. I think in practice it's fan out more of like 32 of 6 or 64. So the tree is only kind of like 2 or 3 levels in practice. But this is also kind of just a way of trying to optimize kind of how do we get the data from the blockchain to people as fast as possible. And so that once you collect enough shreds from this turbine tree, you can reconstruct the block. And yeah, so it's kind of just the flip side of being very intentional on the both kind of incoming side and outgoing side of how the network is treated. Cool.
So preferring high stake is like a little bit of a rich get richer effect, right?
It is, yeah. I mean, so that's definitely true. So if you're like a trading type entity where you want to get information faster, then you definitely want to get more stake. So the new version of Rotor kind of helps with this a bit, and that like there's a bit less incentive to be higher staked. It is true with kind of like there's multiple levels of the tree. People that want information faster definitely do want to be staked. I mean, it doesn't like help you too much beyond that. Like if you're not doing trading type stuff, you'll hear about things, maybe 200 milliseconds later, 400 milliseconds later, which is, not ideal, but for your consumer app, you probably don't care. But yeah, I think this is kind of a tension that's interesting of the network is a resource you need to meter somehow in terms of it's very constrained. And in the absence of like having a chain to run the network on, the only thing you can see that's permissionless is stake, basically. And so when you prioritize stake, then yeah, naturally information both comes from high stake people faster and gets to high stake people faster. To what extent that can be addressed, I think is interesting. Yeah.
And so for Rotor, you're saying everyone's on the same level anyways, so they just get it at the same time, basically?
Right, yeah. So Rotor basically, so here there's kind of like this first node in the tree. And so Rotor's, the reason that first node exists today is that they didn't want the leader to do all the work of the erasure coding and whatnot. So the leader just sends everything to this one guy, and then this one guy does the work of like erasure coding the stuff and sending things on to the next level. So Rotor's basically just going to be just like one level of some set of relays, which I think it's going to be 128 or something like this, and then those relays do kind of all to all. They broadcast their shred to everybody, and so then kind of nobody kind of on the relay level should have enough shreds unless they have lots of stake to reconstruct, and then everybody here is kind of in 2 hops at approximately the same time. Whereas today there's a mix of kind of like data shreds and coding shreds. So some people are getting data shreds, do learn stuff faster than people are getting coding shreds, say. And yeah, so all of this is kind of trying to be fixed in Alpenglow, but for now, this is the current structure.
So you're saying it's both the tweak in how the erasure coding is done plus the flattening of the tree structure.
Yes, exactly.
Okay.
Yep. Okay, cool. So now let's hop into the execution layer. And so I think one important thing to know about Solana is that they have continuous block production. And this really drives kind of a lot of the market structure things we see. And so you normally have this 400 millisecond slot on something like Ethereum, right? Like you'd broadcast the block at the end of the slot. Solana is not like this, right? So kind of here, these boxes represent kind of like mini batches of transactions. And Solana has this like parallel execution environment. So you can think of each of these batches as being kind of a set of transactions that can run in parallel on different threads. And so roughly every 20 milliseconds, the validator is producing a batch of transactions, executing it, and then pushing it through Turbine, right? So we kind of see every 20 milliseconds, it'll kind of run a new batch of transactions and push it through Turbine and kind of go on so and so forth. And so it'll do this until kind of you get to the full block. And so now the important distinction here is that a block is still the full set of things in the 400 millisecond interval, right? So consensus only happens at this level of granularity, right? So the fact that there were these kind of mini, what they call like shreds that were being sent through the network, it is not part of the consensus protocol. It's kind of an implementation detail in that nodes on the receiving end, kind of Turbine is continuously gossiping these like kind of mini batches. And the nodes are continuously receiving these mini batches, re-executing, and keeping up with kind of the tip of the chain in that way. And so other chains would have something like, only this big block over the 400 millisecond interval is kind of all broadcast at once. And everybody starts executing right once they receive that. And then they vote after they execute everything they received. In this case, it's only this last bit, right? So like up to 380 milliseconds, say, you're receiving stuff and you're not voting yet. You're just keeping up with what's in the block so far. And then in the very last bit of the block, kind of the last shred, now you execute that and then you vote immediately after having received kind of the very last bit of the block. And so basically this means that you can kind of just pipeline things much more efficiently, and that instead of kind of fully doing block proposal, then execution, then consensus, these are all kind of interleaved together, where the time between receiving the very last shreds of the block and voting gets very small. So now let's talk a bit more about how this kind of parallel block building actually happens. So this is kind of like a high level overview of kind of what's happening inside the validator, and we'll talk through some of these steps in more detail. But just to get a high level grounding, right? So this transaction ingestion point is kind of this sacred QoS thing I was mentioning, along with some other details in practice. But basically, just it's the validator receiving incoming transactions. And one point also is like here it's like written as one box. In practice, this might be multiple computers, right? Like you might have one server just dealing with transaction ingestion and acting as like a buffer between some other node that's like building execution, just to make sure there's like not one process getting overloaded by everything. But logically, it's kind of all one component, at least controlled by one entity. And yeah, so transaction ingestion is going to just managing like what are all the packets I'm hearing about, all the quick connections, all this type of stuff. And then SIG verify ends up being kind of a fairly big bottleneck. I mean, it's not anymore, but at times it has been. Just signature verification is actually one of the large roadblocks in doing block production. And it's also just because kind of the magnitude of transaction ingestion or the amount of transactions being ingested will be quite a bit larger than what actually gets published at the end. So for example, if you think of the block size as being 100, the validator might hear like 1,000 or 10,000 transactions that want to be included. And so each of those has to be, all of those signatures have to be verified before you start putting them in the rest of the stack. And so that can be a lot, but that can be parallelized, and people have thought about different ways of making this even faster, but something to keep in mind. And so once all the transactions have been kind of verified and deduplicated, they hit what's called the central scheduler. And so this is only kind of like this is basically how the validator just decides how to batch the transactions in a way that they can be parallelly executed. And so we'll talk more about that in a bit. But basically they run some algorithm, take all the incoming transactions, and then they shoot them off to these worker threads, where kind of all these threads kind of execute in parallel and like commit to their values. And then basically the validator just broadcasts everything it's done so far. I know there's another kind of component to this is the notion of a builder, right? So this is going to be part of the MEV pipeline. We'll talk about that a lot more in a bit. But basically, like while this is happening, there's kind of external parties that have a different pipeline instead of the block who are also kind of feeding batches of transactions to the validator to include. At least that's a high-level picture. And so let's talk about the scheduler part for a bit. And so another.
Sorry, Pranav.
Yep.
Do you have an idea of how expensive each of these components are? Like how expensive is SigVerify in comparison to the central scheduler?
Yeah, so not exactly. Do you mean like in terms of milliseconds or?
Percentages, anything? Like how much of signature verification is a bottleneck?
Right. Off the top of my head, no. I know where to look for that. And there are people that have so people have done like the full flame graphs of kind of the full kind of cycle of a client. And so there are dedicated threads. So part of it is that it's not as much a bottleneck, and there's dedicated threads for that. And so while things are being verified, other things are being kind of batched and processed. So my impression is, as of today, it's not that big of a bottleneck. But people have talked about, for example, having FPGAs just for signature verification, where everything that comes in immediately just hits that, and then in parallel you're building the block, and then you can do fancier stuff.
Right, because it feels like a very easy way to do a DOS attack, because you could just send bad signatures, especially at
yes, for sure. That is definitely a concern. Yeah,
Okay.
so that's part of the Sacred QS thing of if you start sending bad signatures, I'm gonna cut you off. I know where you're coming from, and you're a stake person.
Okay, because you have these stake.
Right.
Makes sense.
So it all kind of ties together. But
Gotcha.
Yeah.
Okay.
But also, fees, signatures are handled specially with the transaction fees, right? My sense was the original architecture, they were thought to be most of the computation that was going to happen. Is that right? Or-
Yeah. I think this is the case. Yeah.
Okay. Because you pay per signature in the transaction fee, right?
Right.
I know there's the CU stuff also,
Right.
but I think that came later, maybe? Or?
They're actually, it came later. Yeah. And so one thing is, the difficulty of scheduling transactions, it's not really captured in the CU cost. Or that's just you running some algorithm over the whole set. And so you can run simpler or more crazy ones. So I think that is where the bottlenecks are kind of hard to compare. Running a very expensive knapsack algorithm that's very, very good, then it might actually be that it's much more expensive than signature verification compared to running some very simple greedy algorithm that maybe it's fine. So yeah, on that point for the scheduler, one important thing to note is that in Solana, all transactions are forced to declare every address they will either write or read to ahead of time. And so that lets us build this kind of graph between transactions. So kind of in this picture, think of every node as a transaction, and there's an edge between nodes if they're conflicting. And by conflicting, that means that maybe one node writes to an address and the other one's going to read from that same address. And so in particular, what it means is that these transactions cannot be run in parallel. They have to be run serially. And so we can build this graph, given that people are forced to declare these things kind of upfront. And so then the question is, what do we do with that? And so basically, what you have to do is basically just pick independent sets of this graph, and that's where they're going to be our batches. And so, so also keep in mind this is happening kind of continuously. So transactions are streaming into this kind of set. And also forgot to mention that each of these transactions also has a priority fee attached to it. Right? So Solana kind of has a base fee and a priority fee as its transaction fee mechanism. And so there's roughly the guarantee that the higher your priority fee, the more prioritized you are by the scheduler. Now, that's not enshrined in any strong sense. That's kind of a rough guarantee the protocol gives you. And the reason it's not enshrined is kind of because of this reason of that you're picking independent sets of this graph, kind of as your batches and your ordering. And so it's not super well defined what it means if, I have a very high transaction fee, but I'm conflicting with lots of people, and somebody else has a very low transaction fee, and they're not conflicting with people, of who exactly should be ordered in what sense. And if there's some path between these two transactions in terms of conflicts, then it gets more tricky of what guarantee you actually want to make. There is no strong guarantee, but roughly the algorithm that the default client uses will be to make some priority queue type structure, and trying to pick the highest priority fee transactions at any given point that it can, and then putting sets of those that can be parallel executed into a batch, and then kind of shipping that off to the worker threads.
Yep. Did people consider running a more sophisticated maximal independent set algorithm? Just
so it turns out this actually is a bottleneck in practice with just the sizes, number of transactions going and how fast things are. So yeah, so it's a streaming algorithm going in 20 milliseconds with, not crazy high number of transactions, but a reasonably high number of transactions. And so even unsophisticated algorithms that were just build a DAG and pick kind of the highest things in the DAG that seemed you could do at the same time. Turns out even sorting was too slow or something. So now it's I think as of very recently the default client uses this a pure greedy algorithm, And just in terms of like speed, this gets you enough where the throughput's just meaningfully higher, and that's actually more revenue than doing the things slower that are more sophisticated algorithms. Now, of course, you can attack these, right? Like if I know the algorithm, I can give you very, very bad inputs. That's a problem. In practice today, lots of the validators run their own custom software here, right? So the default client has some greedy algorithm. People optimize their revenue by doing all sorts of things, as you can imagine, running better algorithms here.
There's the classical randomized algorithm, just like each. No, okay, yeah,
Sure,
we can talk offline.
You're not worried about MEV here, or?
I am, yeah. So I'll go to that in a bit. So the MEV stuff actually goes through a different pipeline, kind of. It very much is a concern. But for now, assume it doesn't exist. Even then, it's still kind of a hard problem of how do you build these blocks fast. And yeah, so the other main thing to mention here is that Solana has this notion of what they call local fee markets, which you can basically think of as these multi-dimensional knapsack constraints, where there's a global kind of CU limit. So in Solana, CU is equivalent of gas. Right, so they meter all the computation in CU. And so there's one big global CU limit. And additionally, every account has its own kind of local CU limit. And that since we have these kind of read-write lists for all the accounts, you can track kind of how many transactions interact with an account in any given block. And there's a constraint that basically, only some fraction of the block can be touching the same account. And the point of this is that since we have this parallel execution environment, we want to try to incentivize workloads that really can be parallelly executed. And so the kind of this local fee market structure is kind of what allows for that. And having these kind of knapsack constraints that on the accounts that are smaller than the total limit means that like kind of if there's tons of demand on a single account, say for some NFT drop or some price movement, you won't have that the entire block gets taken up only by these types of transactions, in which case it'd be kind of a fully serial workload. You kind of enforce that like at most kind of like one thread is focused on these transactions, and the other threads are free to pick up kind of things like simple payments, other applications and stuff like this. And I think it's a bit helpful here to get a bit more into the math than the other parts of it, so it's not too bad to express.
Quick question first.
Yep.
Do you ever see people in practice like splitting an NFT mint over 4 contracts in order to like saturate all 4?
I don't think so. It's been a while since like the NFT meta, honestly. So actually for separate
or any other application, obviously, right? But it's not clear that's bad because you're basically making the app layer conform into being a parallel workload, right?
Right.
So it's not clear.
Exactly.
Yeah. Okay.
Yeah. So for a lot of finance things, it's hard, right? Like if I need to interact with a price, then like this price better be in one spot.
Yeah.
I'd say that's the majority of the demand that like hits these constraints. But it is true, like when you're building things like order books and whatnot, like you should be very aware of like this is how it works, right? So like your order book should split up your assets across different accounts in a way where you're not all hitting the same thing, which is good, right? Yeah, so now you are incentivized to actually have these kind of high demand applications, really so that the workflows in different ways that can be parallelized. But yeah, so like the formal way to define this would just be that kind of you have some set T of total transactions in the block, where every transaction has some like amount of usage and some kind of account list, and you have one binding constraint on kind of the total amount of compute usage in the block, and then for every single account you check that kind of its local limit is also not being hit. And yeah, I think the main kind of takeaway here beyond the details is that specific accounts can be kind of at capacity in terms of demand, while global block space is not at demand, right? And so this is what kind of it means in the sense of that something like an NFT airdrop or like something like some massive like ETH price or SOL price movement will not make the chain unusable, at least at the execution layer for other types of transactions. And they should always be able to get something like a payment through for a very cheap fee. And I think one thing also to make sure it's clear, though, I was kind of confused by initially, is that local fee markets aren't implemented beyond this, right? So there's no notion of a base fee per account in Solana, right? So the transaction mechanism is still just a fixed kind of base fee that's pretty nominal, and then an optional priority fee. And basically the way the different fees come from different types of accounts is that the equilibrium prices are going to be different depending on the demand for that part of state, right? So if kind of the total demand for block space is a decent bit below the total capacity, then normal transactions are basically just paying the base fee and like maybe a very, very tiny tip. Whereas at the same time, there's transactions that are interacting with a very highly contested piece of state that really is at capacity. then those are basically competing in effectively a first price auction, where they're kind of trying to outbid each other to be the ones that get in kind of out of the fixed supply, even though there's kind of other supply that they can't interact with.
Yeah, I feel like local gas limits would be more accurate than local fee markets.
Right,
Yeah.
right. Yeah, so the market is purely kind of a function of kind of the wallets and traders bidding with the kind of local gas limits. And there's nothing in protocol that actually says that like there is this price for a certain piece of state. Yeah, and so to see how this looks kind of practically, here's a graph from the Fire Dancer team. They have this nice dashboard where I'll just show you the actual dashboard. It's kind of cool. So they basically made this thing that basically allows you to see, based on what their client is doing, kind of how the transaction flow looks like. And so here you can, for instance, see kind of like this intro to the pool of the quick transactions. It's like 192,000 transactions, which is kind of crazy. And now these are almost all duplicates, just because of how like this network is handling things, or how people are kind of double sending things in various places just to get it to the validator. So in the end, it's only this like 1,600 transactions of which lots are votes. But yeah, so this is kind of the level of demand that the network has to deal with, and that things like signature verification, like here it's like these all, almost 200,000 transactions, being verified. And then, as you get through the pipeline, more and more things get thrown out until the very end. And just to see what the continuous block production looks like, this pink line is the amount of CU kind of throughout the slot that's been processed, right? So here we see this is a slot from 0 to 400 milliseconds. You can ignore some of the other lines. Some of them are kind of with fees and some other just artifacts. But you can see kind of in the Ethereum talk, I talked a bit about these timing games, and then people kind of wait towards the end of a slot to bid really high. And you can see a similar thing, at least in the Fire Dancer client. The CU is increasing at a pretty steady pace, and then really right in the end, in the last 50 milliseconds, they're doing almost all their work in the block and like kind of filling up the block to capacity. And this is kind of just natural. You can imagine kind of any streaming algorithm, like the longer you wait, the more information you'll have, kind of like the better optimization you'll do. Instead of kind of committing to actions early in the slot by filling up lots of your block, you want to wait till the end of the slot to hear as much as you can, and make sure you're not kind of excluding any valuable transactions you might have otherwise.
So going back to the shreds picture, you're basically saying it's only the last few shreds have all the good stuff, basically.
Maybe not, but you want to just make sure that you don't commit ahead of time anyways.
But you're not going to be transactions.
Oh, right,
you are
shreds,
sending
right.
shreds every 20 milliseconds.
Right, yes,
right?
yeah. So the last shreds will be lots of the, well, it's also like these fee charts can look different. So the blue line here is actually the fees. And so here, it is actually the case that the fees at the end of the slot get really high. You can see if I look through some other ones, it's not always the case. So here it's less the case of like the fees are jumping earlier in the slot. Let's see if I can find another block.
What I'm trying to understand is the pink line, the CU line.
Right, yeah. So at least the majority of the CU will be at the end of the block. It's not necessarily the majority of the fees, though. So what like good stuff means, I guess, depends on what you're looking
that does
for.
mean the shreds toward the end have more stuff in them than the shreds earlier on.
Yes,
basically, right?
more stuff. Not necessarily better stuff,
Yeah.
but just
well,
more
yeah,
stuff.
because the top of block MEV goes in shred 1, I guess,
Right,
for example,
right,
Okay.
right.
Yeah, isn't this MEV motivation to actually surprise people at the end instead
Yes.
of giving them a lot of time? So maybe that's the reason.
Right, yeah, that's another reason, yeah. And it's just, the MEV pipeline is a bit different too. So the block packing is partly done by the validator and partly done by other people, and we'll talk about that actually. Yeah, maybe I'll get to that first, and then we can get back to that point.
But so your hypothesis would be that is the reason, that basically if I have something that I'm worried about being sandwiched, I would try to send it at the end, and then there's a larger competition on the end in some sense?
Probably not. I think it really is that like there's lots of low value transactions and lots of just medium value stuff that the validator might as well just wait. I think things are being sent earlier probably. So there is a way to express. I mean, this all like kind of depends on exactly what validator somebody's running and what MEV infra they're running. But if you want something to happen like right now, like there's ways to do that. Or there's infra, at least in theory, that does that. And to what extent that maps into practical guarantees, I think it's not obvious. But like if I wanted to trade at the beginning of a slot, then you can make that happen. And so people do wait towards the end of a slot. So this graph looks different depending on the validator that's running. So this is the curve Firedancer decided was making them the most money, to wait towards this kind of last 15 milliseconds to like pack a lot of the block. Some people will kind of just follow a more linear path through this. If they can linearly include transactions as they can until the end of the slot. But yeah, I mean, it's right that, yeah. So for MEV reasons, like generally you want to send at the end of the slot. The continuous block production is what makes that less obvious of exactly how that works. Whereas the validator made a commitment to, I will be literally flat until the last 15 milliseconds, now literally nothing. Then that would certainly be the case, and you would certainly expect to see this behavior. But the fact that stuff is being executed before makes it a bit harder to reason about.
I guess your point is, I mean, even setting aside MEV, a really simple theory for what's going on at the end is just you don't know what the market clearing price
Right.
is for transactions
Yes,
in the block.
exactly. Yeah.
So you see 3 cents and you're like, should that get in or not? I don't know yet.
Right. Yes.
And so you just wait till the end.
Right. Yeah. So I think that's what this mainly
That
explains.
makes sense. That makes sense.
You can think of this as like kind of an online knapsack algorithm, where the more things you see, the better you can pack. Instead of the packing half your knapsack at second, or millisecond 100, and then you see all this very valuable stuff come in millisecond 200 for whatever reason, some price moved, and now you just kind of lost money for stuff that you could conclude otherwise.
So it'd be different if every shred actually, had to spend, like if you spread the CU budget equally across the 20 shreds or whatever,
Yes.
that would be different, right?
Yes.
Because then you
Right.
would see the,
Right. So that's almost like making the block time 20 milliseconds, you could think of, which you could do. Although it's hard to enforce without making the consensus time at that level. But yeah, so I mean, so this is things people are talking about, like let's make the block times. So one other detail I forgot to mention is that in Solana, the same validator controls 4 slots in a row, right? And so you can ask like, why is that? One reason is kind of this for these performance reasons of, like if you could have the validator make, 10 blocks in a row, but they were all 30 millisecond blocks, it's like just different kind of performance trade-offs. And that like now, with 4 blocks in a row at 400 milliseconds, there's lots of games they can play with kind of, between, their second and third block or something. There's all these timing games that can happen. There's lots of annoying stuff. What it means is that leader rotation happens less frequently, while consensus is still pretty fast. And so, like every 20 milliseconds, you get some kind of mini confirmation. I mean, there's something behind it, but it's something that, at least statistically, like tends to mean that you're included. And then every 400 milliseconds, you have a consensus process. And then, every 1.6 seconds, you hand over leaders between people. And you're just like, as you can imagine, leader rotation is pretty expensive. You have to like kind of move all these transactions in your state to the next guy before they can start running things. And so these are all kind of things that might change in OpenGlow. These might change in general, and that people are kind of discussing are important things to think about for any chain, really.
Can you go back for a second to this like graph that shows the amount of duplicate transactions? Is there a reason why you verify the signatures before you filter out the duplicates?
Yeah, so there's actually 2 tiers of duplicate. So like there's this first one and then there's second one. I don't know the engineering details behind this. Presumably there's like, even on the network layer, you get like the exact same packets. Just from like different sources, maybe, or something. And then like once you actually verify the signature and like it's a real transaction, there's some more thorough check for like it's formatted correctly or something. And even then, it's the same thing. But yeah, I'm not entirely sure. Okay, yeah, so now let's talk about MEV. And so just to remind people, kind of a primitive of kind of the MEV pipeline is this notion of a block builder auction. And so you recall, basically people are allowed to submit bids that are arbitrary functions of state. Where basically just kind of the way it's implemented is kind of like the last kind of function call or last kind of transaction in the bundle. This is just transferring some soul to some address that the builder interprets as a payment to them. And then basically the builders are just using heuristics to decide the optimal ordering, right? So in this picture, you can think of F, G, and H as being kind of different functions, representing bids over state. And now the builder is just trying all these different orders of F, G, and H, and it finds the order that maximizes their profit, basically. So this is kind of just like a black box thing that in Ethereum is the whole block builder auction, and in Solana it's going to be kind of a subcomponent of a broader stack. And yeah, so just recall, so this is an Ethereum thing, not a Solana transaction, but the concept is very similar, where you have some transaction, and just like the last function call is just a transfer of some amount to some address. So think of this as a very general kind of bidding language that people can express. Okay, and so we're going to call this kind of a state auction of just as one of these primitives that given some inputs, you run this process and out comes some ordering of these transactions or some subset of transactions. What happens, so I'm going to describe the Jito auction. Jito is what kind of builds most of the blocks in Solana. There's a couple other ones more recently, but in the interest of time and clarity, we're going to focus on the Jito one. And so what happens is kind of similar to central scheduler. People will input kind of transactions and bundles, and will similarly form a graph between them, where the same kind of read-write graph of two bundles conflict if they're touching the same piece of memory, writing and reading from the same thing, right? So then basically what the auction does is going to basically take the connected components of this graph and then split them up into different pieces. And so now we have the very nice guarantee that whatever I do in one piece won't affect another piece, right? Whatever the outcome of the auction on this blue state is not going to affect the outcome of the auction on the green state because the transactions aren't interacting with the same pieces of memory. And so basically what I'll do then, I'll just run this kind of block auction, or call it state auction, that we just defined on each of these individual components, right? So now in each of the individual components, I'll get some subset of those transactions, and I'll have some ordering between them. And then basically the block builder will put that whole thing into a batch, right? And so you can think of it as very similar to like the Ethereum process, except motivating by the fact that Solana anyways has this parallel execution environment. You can do things a bit more efficiently using that information and run these kind of parallel auctions at the same time. Now you might ask, like, what if I just throw in kind of random garbage transactions to connect these pieces? You can totally do that. There's also ways to game this thing. It's very much a heuristics-based mechanism and does not have like a very clean, kind of functional form or kind of allocation and payment rule. So also it's kind of pay as bid based on what you set to bid. So people do all kinds of games here of spamming this auction. Like Jito has lots and lots of infrastructure kind of to make sure that people can't spam this too much and kind of deprioritize people who are kind of just explicitly messing with this thing of like connecting components and just kind of overall being nuisance to execute. So it is fairly permissioned of like this is all kind of happening inside this builder box that is just basically what Jito runs. And so for things that are MEV transactions, oftentimes, you directly send to the builder. Sometimes you'll send to the builder and the validator, or like many places, and we'll talk about that in a bit. But yeah, so you can overall think of this kind of builder box as effectively running the same thing as like an Ethereum-style block building auction, just using the Solana semantics and being much faster, right? So the same kind of streaming thing we had before still applies here, where one thing to note is like the block never stops for the block builder, right? So in the Ethereum context, it's like nothing is happening, right? Nobody's committing anything. Just like transactions are coming in, a block builder auction happens, they decide the optimal ordering, and then they give that to the leader. And importantly, kind of like the leader there has full view over the state, or what they're executing on. This is not going to be the case in general in Ethereum or in Solana, where the scheduler is never pausing for the block builder. It's just that the builder's batches get priority on the scheduler. And so the way this might look like in practice is something like this, right? Of like the scheduler is doing their thing, they're making these batches, they're sending these transactions that can be run in parallel, and then the builder basically lets to like kind of pop their stuff ahead to the front of the queue. And so the builder is sometimes part of the scheduler. So there's some or many nuances here, and that sometimes the builder tells the scheduler, hey, I'm running auctions over these accounts, please lock them, don't build batches for these accounts. And then once the builder auction happens and finishes, it schedules those transactions, and then those accounts get unlocked. So the exact interplay between the central scheduler and the builder is kind of, it's pretty delicate in terms of like who is grabbing locks when, kind of how much time advantage does the builder have in grabbing these locks. So as you can imagine, it's a very complicated system where, again, there's weak guarantees you can get, but there is no kind of clean description. A lot of how this plays out is just really like just engineering choices, kind of dictating market structure, and just iterating of like as people find ways to break it, they find ways to fix it. It's kind of a cat and mouse game. But at least at a high level, this is what's happening. There's a stream of transactions you can think of as generally being fairly simple, going to the validator, and then they schedule themselves with some greedy type thing. And then the more complicated preferences that are much higher in volume go to one of Jito's, few data centers. They try to run this auction, get stuff around the world, and then they you have much more compute to be running these kind of just different heuristics to build these blocks optimally. And then they forward those batches to the validators. And so in the Ethereum world, the validators themselves don't run a special client, right? They run their standard clients, and they run MebBoost as a sidecar to kind of hear about these blocks and sign off on them. On Solana, people actually run the like Jito Solana client, right? So you run kind of a fork of the default client that has this builder integration into it, which lets the builder talk to the client very easily and kind of get these transactions in, these batches in, and that's what makes this whole thing work. It's all a much more synchronous process than what happens on Ethereum, for example. Now, this is being changed a bit as of like very recently. There's this thing called scheduler bindings, which try to break this up and don't actually require that like to be running Jito, you have to run the Jito Solana client. As you can imagine, that's very annoying. Anytime the default client ships any kind of like patch fix or any type of hot fix or something, the Jito client has to be kind of updating at the exact same pace. So that leads to security issues and vulnerabilities and just overall headache, DevX and kind of DevOps wise. And so they're trying to change it, or maybe already be live, where the scheduler now just has kind of like JSON interface with the builder, and the builder can just stream transactions indirectly instead of having a more complicated integrated client. But yeah, just some other details that aren't super relevant.
Are the batches that the builder submits, is it supposed to be like an atomic bundle, the same way like searcher bundles are?
Yes, it is. Yes.
So they're generally not, they're going to be executed on a single thread,
Yes.
kind of in the same order that was suggested?
Yes.
Okay.
Yeah.
And in principle, the validator could modify the Solana Jito client to unbundle
Yes,
those.
they could.
Okay.
Yes, which would be pretty bad. I'm not sure to what extent that already happens, but yeah, it's like a very different trust model than the Ethereum world, and that validators totally could unbundle people. So being a Jito, Jito sending you stuff is like not also kind of permissioned. Of like most people have access to it, but if you did start doing very bad stuff, they can just stop sending you things, and then you'd be kicked out of the network basically.
So there's no like relay in the middle.
There is not. Yeah. So Ethereum has the relays to protect everybody, and as long as you trust the relay, everybody can be pretty happy. Things are just moving too fast for that in this world of like the relay only works because of the asynchronous nature of things of like it's builder moves, relay confirms, they send a proposer, then proposer confirms and things happen. When everybody is continuously kind of moving and like producing stuff, there's just, it doesn't quite as much make sense to have some relay in the middle kind of managing the whole process.
How many builders are there in Solana?
Really one. Kind of two now. I mean, there's a few more. So like the way builder is defined is a bit different, in that like it's not so. Also worth saying, kind of Jito only builds something like 20% of the block today, right? So a lot of the block is still going through the central scheduler. It's just the high value stuff that Jito is building, and so it's not the model of like the builder does everything and hands off everything to the scheduler. It's like the builder does some stuff, and now this is also changing. So there are some worlds where like it might be the case Jito is really building the entire block in the future, but at least as of a few months ago, Jito is only building part of the block. And so there, the notion of builder centralization is not as bad in that like if the validator includes you, the builder can't stop the validator from including you, which is not the case in Ethereum, right? In Ethereum, if the builder doesn't include you, then you don't get included. And so there's different types. It's even possible for multiple builders in practice to be on the same validator in Solana, right? Like you imagine two of these boxes streaming batches, and then the incentives get kind of weird of how that actually works. But that kind of is how it works in some cases. But really there's one, kind of two. Now there's, I think it'd be fair to say there's two now, but Jito is a dominant player, at least for the Solana world.
And is there some like revenue share mechanism between
There
the
is,
builders and the validators?
Yeah, there is.
I see.
I forget exactly how it works. I think so. Yeah, and Jito takes some cut. A lot of it goes to the validators and to their stakers even.
You said we run a few block auctions in parallel.
Yeah.
How do we decide how many when?
Yeah, that's like an algorithmic thing basically. Like how far down the tree can you search fast enough? So it used to be pretty shallow. It used to be like one or two. I think these days it's higher. I forget the exact numbers. Maybe like 3 or 4 per block auction. But that's purely on Jito's side of like how much can they simulate in these time frames and send it off to the validator in time.
So what is the incentive for the central scheduler to be doing anything as about like what why should a validator run this if it's such low value transactions?
Yeah, I mean, so sometimes there are high value stuff going through it. So like this whole process is very jittery. It's kind of what they say, and that like since it's all being continuous, like you might have just missed the Jito auction window, and so sometimes you send to both. Right? Actually, very often you'll send to both central scheduler and to the Jito auction, just to like maximize your chance of landing. Yeah, this whole process is so messy, and there's so many competing things of like, did your packet hit the leader in time? Did it get through SIG verify in time? Did the scheduler in time? Did the scheduler have the lock to let you in? Does Jito have the lock? Like, who has the lock? And then it's like, just to maximize your chance of getting in, people just send everywhere to everything. So the central scheduler actually still does a decent amount of work in like getting valuable transactions on chain. Okay, and yeah, just kind of the last thing here is this thing that's called a transaction landing service that's become more popular because of exactly kind of this point. And that you can imagine it's like a very hard problem to decide like what RPC do I send to that has enough stake? Do I send multiple RPCs? Do I send to Jito directly? Do I send to somebody else? Do I send to like the validator's port directly? There's like many options as kind of a user and how you submit transactions on chain, and really more as like a wallet, or like it's like a a more sophisticated trader of options to land on chain. Like as a user, you're probably just like clicking some button and then like that app is like deciding on your behalf how this thing gets sent out. And so there's been lots of instances of like people being very frustrated with their apps, like not landing transactions, right? Like you can imagine, some meeting point thing is happening and I'm trying to trade it. And just all my transactions are failing and I'm very upset as like a retail user. And so these transaction landing services have come up, which basically like their whole job is like a wrapper around this entire thing of you give them some tip and then they split up your tip amongst the priority fee to the validator or some like Jito tip or like kind of some mixture of tips, different people. And yeah, so point being, it's a very messy game. There's a lot of stuff happening. And so the transaction landing services have come up as kind of a natural way to abstract it away for like the average person. Of course, now that's just one more part of the stack. And so everything else is messier. But yeah, we'll expect to see more and more stuff like that, at least kind of in the short to medium run.
So should I think of Phantom as a landing service, or they would use a
No,
landing service?
they would use a landing service. Yeah.
Have you ever heard of any landing services?
Yeah. So what can I say?
Are there any? Is there like a biggest one with a name or?
I don't think so. I don't know that I can say it.
Okay.
But yeah. Yeah.
Few coming attractions, you're saying?
Yes.
Okay.
Yeah.
Okay.
So do they create bundles with your transaction? So you gave them some tip. So now it's not like they can modify your signed transaction. They need to create bundles now, right?
Yeah. So I think it's some notion of bundle. I actually don't know the exact details of how it works under the hood, but something like that seems reasonable. Just takeaways now. So yeah, this is kind of the whole supply chain. One main thing is that there's like two main points transactions can be dropped, right? So one is at the network layer. And right, so there's tons of things that are competing for space and kind of the entry for a validator. And so even like getting through that can be tough, right? There's like the Jito stuff and like the normal entry points and whatnot. And then the scheduler, right? Of like all these locks make things very awkward of like, even if you have a higher priority fee than some other transaction you're competing with, if you hit the, scheduler at just like the wrong time, the scheduler just like doing some round robin thing in a weird way, your transaction can be dropped for just all these types of reasons. And so when you're building applications on Solana, like reasoning about this is pretty important. And this is why it's kind of very messy. It's very annoying for people to interact with sometimes. But yeah, so there's that to know. The upside of this is that, if you are doing non-contentious stuff, like just simple peer-to-peer transfers, that the kind of local fee model and parallel execution means you should have pretty good guarantees actually. Like as long as you can get into the box, you probably should make it through the whole thing of there's not much standing in your way. It's really the combination of the networking and the locks that make contentious transactions hard to land. And this is because the continuous local building, if you had a more Ethereum style thing of, hey, we're going to stop block production for like, 200 milliseconds, and then we're going to run some auction, and then the output of that are the transactions that are included. Like now it's much easier to reason about what's happening. It's really the fact that everything is continuously happening, that you don't have a clear interface to interact with, and that people are continuously changing how they're doing things. That make it pretty annoying. And so one thing that's like a design thing Solana shows is that they basically, for all these reasons, push complexity onto the users instead of kind of dealing with it themselves, right? So things like declaring these read-write account lists, having this first price auction instead of kind of base fees per state, kind of like having this continuous building model. These all make it like pretty hard for users to reason about. And that's kind of on purpose to make the protocol itself very efficient and very fast, which it is. But this is just a trade-off you can make as a chain, right? You could not make these choices and you could be a bit slower and you could give users a much cleaner UX at the cost of some of these efficiencies. There's something to keep in mind. And yeah, just in general, I think this is how this has all played out over the past kind of couple of years now. Just shows like how hard maintaining clean supply chains is for these blockchains, right? So kind of today, it's really only Ethereum and Solana that have had to deal with this in a meaningful way. That's kind of like decentralized chains with lots of usage that kind of necessitates the need for all these parties to spring up. And yeah, so I think there's basically, for chains in the future, other applications should just be aware of like, this will happen eventually. Kind of once you get enough users, the demand is there, and then it just really is hard to serve all this demand with like a very clean chain. And so making choices at your infrastructure layers and application layers to keep this kind of system as clean as possible is always good. Yeah, and I'll leave it at what the future of Solana might look like. Something we've been talking a lot about here is Alpenglow. And changing, it won't change any of the stuff I talked about kind of too much immediately. I'd say the biggest thing is it makes everything just cleaner, right? So everything I said is true, and then there's like Tower BFT today that makes it even worse of the reasoning about like how things happen. Things like, one thing I mentioned is that votes are transactions, for example. So votes are forced to go through the same pipeline, and they're given easy entry, at least in theory, but there's even problems there. So all the stuff around that, just the easier consensus is to reason about, the easier everything else is to reason about. So that'll be good to see. Then things like bigger blocks help. Async execution, so like so here would be moving away from continuous execution and continuous just proposals still. But you only execute kind of after the slot ends, say, or this is even kind of less of a blocker.
Wait, so with async X, does the 20 millisecond thing still make sense?
Yeah, so there's different versions of this. So one version is just you're allowed to vote before executing. And so you save like 20 milliseconds there basically. And like the very last shred you don't execute, you just immediately vote on. And things like leader rotation become a bit easier. So here it's like by moving execution off the hot path, you can basically have people continuously proposing the 20 millisecond sub blocks. Sure. And like it's fine. Like nobody gets slowed down at some point to like run the last bit of a block, then vote in it, then do something else. You're just like in parallel voting from executing.
So you were saying you would vote every 20 milliseconds now?
No, so you would still vote every 400 milliseconds. But right now there's like an awkward thing of like between me receiving the like last shred of a block, I have to like reconstruct that shred. Well, so I still reconstruct that shred. Now I have to like execute it as well. And if there's a leader rotation happening, it's kind of even more annoying. Like the next leader has to like wait to get that and then start proposing their blocks. With async, that would be less of a concern. So like today, like blocks are only valid if they meet all these conditions of like, you can't have missing transaction fees, you can't have like certain transactions failed, or otherwise the whole block is invalid. And so that means, for example, like the next leader can't start making their blocks until they receive and execute the previous set.
I see.
And so, at least for now, async execution just helps. Like, it's a marginal change today. The hope is for doing MCP type stuff, it's actually like a requirement. So making it the protocol now changes the market structure a tiny bit today for the better for the most part. It's more just a cleanliness and kind of like quality of life thing. But yeah. So it's not a major thing today, but it could be in the future. And that's really, so MCP is basically this proposal that makes reasoning about transaction inclusion much easier by kind of taking away the power of block building and this execution stuff. And so I won't go too much into other things. So the application control execution is that the sequence of transactions can depend on kind of the applications can choose their ordering instead of kind of the leaders choosing ordering, basically. 00 is a networking thing that should make some networking problems easier. We can pipeline this up even more in some different ways. Different ways of charging fees that can help some of these estimation problems. So lots of stuff happening. Solana stuff changes like literally every month. So some of this stuff might be outdated very soon, but at least at the high level picture, I think is a good conceptual framework, and definitely at least lots of takeaways for future projects. So yeah, I'll leave it at that.
Looking at the two example, like big example like Ethereum Solana, are there some interesting invariant that are building? Like you pose a really good question that as chain grows, they have to think about these things, which if they're not thinking, are there simple invariant, is it that your latency is always going to slow down because you have to add some proportion between, what are the general lemmas or something emerging here?
Right. Yeah. So I think that's a good one. That like latency, so like optimistic latency is very hard, and that you basically always get the worst case latency that people are incentivized to give. Right. So MEV basically pushes people making choices about state to wait as long as possible. So latency is one of them. Other invariant. Just like inclusion always gets harder, right? And like reasoning about. So I think one thing I think on blockchains a lot is like, hey, we have a fee mechanism. We'll use that to meter things. I think understanding the network layer is very important. And oftentimes your network layer will be the first to go down before even the fee mechanism gets hit. For example, if I can DOS your nodes so that they don't even hear about the high fee paying transactions I can get in, right? And so knowing what to do on that level is pretty tricky. It's not immediately obvious. You just depends on your chain of how you address this. So maybe that like the network layer gets very hard. Everything else, once you get past network layer, you can deal with stuff inside the protocol. But before that, it's pretty tricky.
Can you expand a tiny bit on application controlled execution? What is that?
Yeah. So this is not a fully fleshed out proposal. But so one example of this is this notion of kind of MEV taxes and priority ordering. So say I give you that I force all the transactions to be ordered by priority fee in your block. And now as an application, say like I'm some exchange or something, or say I'm an AMM, and I say you can only submit a trade if your priority fee is below this amount. If your priority fee is above this amount, then I only allow you to like either deposit or withdraw like kind of LP funds, like move like the LP position. Right, so this means that basically if I submit a priority fee above this threshold, then I'm guaranteed to like change my position in the AMM before anybody gets a trade in the AMM. Right, so this is a way that the application can control its execution, be controlling its ordering. So that's like the simplest way that's fully fleshed out of how you could do it. There's other like feature flag type stuff you can do of like the application just says, so the way they were thinking of doing it is kind of at the level of the block builder or the validator client. Certain applications could tell the client, hey, I want you to order things in this way, and the client would just do it in that way of like, basically that central scheduler would just like have more information about what applications, transactions you're interacting with and schedule accordingly. Now that's not a robust solution at all, but that's at least the type of thing you'd want to implement. And it's, I'd say active work in progress to figure out what's the best way to get there.
That's good.